Ready to double it up? We're going to talk about special reactions that apply to diols. We've actually made diols specifically before. Let's remind ourselves of that. If we start with an alkene, we can arrive at a syn diol, for that matter, or even an anti-diol. What did we need to do that? Remember, syn diol was osmium tetroxide or KMnO4. So I had to lock it into that ring to get those OHs to come up on the same side. Anti was when we had an epoxide, then the new OH attacked from the bottom and opened up the epoxide. So we have the anti configuration. So your epoxidizing agent, your peroxy acid, followed by acid or basic workup, their anti-diol. So we know how to make anti-diols, we know how to make syn diols from an alkene. Now, here's some things we could do to react them. We can do what's called periotic. So periotic acid is HiO4. That's extra oxygens in there. Per means that extra oxygen is present, like peroxy acid or peroxy hydrogen peroxide. Periotic cleavage. That means we're breaking up a diol and oxidizing it at the same time. So sometimes they're also called glycol, but notice that we've oxidized and broken the pi bond, not the pi bond. It's glycosanolysis, an oxidizing agent that does oxidative cleavage, right? Except for it doesn't have a pi bond. I'm going to show the one mechanistic step that helps illustrate product formation. You need these diols in order for this to work. They need to be able to be rotated into a syn position. So even if you made an anti-diol, you just have to rotate it so it's syn. If it's in a ring and it's anti, you're out of luck. It's not going to happen. If it's a ring and it's fixed syn, you can do this. If you're not in a ring, you can always rotate, right? So syn, they need to be syn. And this mechanistic step here, I'm just skipping ahead because this is one we're not showing the whole thing for, but this helps you understand this beast that I'm drawing in, this intermediate, why it has to be syn. We have to get them into a ring, a small ring, 5-membered ring, and that does not happen in an anti orientation, right? You can't facilitate a ring closure if they're fixed anti. So I like this particular step of the mechanism because not only does it show why it needs to be syn, right? It also shows how the cleavage happens, how we cut the carbon-carbon bond and form the double bonds. So right here, so this is the bond that's cut. You can see that arrow showing the electrons being taken away. Bond doesn't exist anymore. It's now part of this pi bond. This pi bond just formed. This iodine, it lost some electrons as it did that, so we actually give them back and with that arrow. So 3 arrows. So what we get there is our new carbonyls with 2 molecules. 1 molecule went to 2. So this is the key mechanistic step. And because it is a 5-membered ring, it must be syn. Okay, so this is kind of fun. I want you to try this example. This is roadmap synthesis. Pause. This is our final end goal. Ooh, there's 2 carbonyls, but they're together. So that means we probably had the diol in a ring as opposed to not in a ring, right? Because if it wasn't in a ring, we'd cut them into 2 separate pieces. But because they're together, they must have been in a ring. So here's our diol I want you to draw, and I want you to come back to the original alkene so we can put this all together. So I suggest you pause now, try to fill it out. I'm going to keep going so that you can get the answer when you're ready. Okay, so I'm going to count carbons. That's always recommended. 1, 2, 3, 4, 5. Okay, so I must have had, if I cut that into 2 pieces, I must have had a syn diol, right? Because the roadmap is requiring me to come up with a diol. So if I had a diol and I made 2 carbonyls, I must have had a syn diol with 5 carbons. So if I have that in a ring, It's in a ring because they never got detached like in the example above. I need to cleave the 1 and 5, right? So that means that's where my diols will be. And they need to be syn. So I'm just going to draw them both on wedges. So I'm going to use HiO4. We just learned about that. That's a hint that should probably be included here. Okay, how did we get there from an alkene? So the alkene would have looked like this. And what do we know that makes syn diols? OSO4, right? Work. 1-OSO4, and then followed by the reductive workup, NaHSO3. You might say, hey, why 2 steps? I could have done this with ozonolysis. Yes, you could have. That's why I don't think this is what we'd practically do synthetically. It would only be useful to use HiO4 if we arrived at the diol, and that's what we needed to work with. We're forced to work with a diol. What if we, instead of adding OSO4, we added MCPBA, right? That's step 1. And step 2, we added OH minus H2O. We would get our anti-diol, right? If I try to do periodic acid on that, because it's in a ring, no reaction. We cannot rotate it when it's in a ring to be syn, so we're stuck. So it's kind of a fun oxidative cleavage reaction for us, syn diols only. Anti-diols not allowed. One more for diols only, called the pinnacle rearrangement. Pinnacle rearrangement. Look at what we got here. Here's our diol. This specific molecule is actually called pinnacle, but it refers to any 1,2 diol that also has a methyl or alkyl attached. 1,2 diol with Me or alkyl group attached. So you'll see this happen by alkyl. It could also do a ring expansion or methyl shift. So the specific molecule is pinnacle, which is why I'm showing it, because historically this is where it was started with. But look at what's going on here. We did a rearrangement, which is why I mentioned ring expansion. We did a rearrangement. And we not only lost one of our oxygens as water, we oxidized one of them to the ketone. By the way, I should mention that contraction's also okay, or just depending on the scenario. Contraction. I'll give you an example of that after. Let's do the mechanism of this though. That deserves a mechanism. And it's a good one. It's good practice putting together all the concepts. It's not a crazy out of left field mechanism. It's actually something you could probably have come up with if you pause and work on it, which I don't think is a bad idea, to be honest. Okay, sulfuric acid. What does sulfuric acid do to alcohols? It protonates them. Choose an alcohol, any alcohol. We're going to protonate it. We're not going to do both at the same time. We're just going to do one at a time because that's not favored to have all those charges. We know we have to lose water. Might as well do it now. There it goes. So I might draw water coming off and even put a minus there, minus H2O. And here is our tertiary carbocation. Stop. We know there's a rearrangement just by inspection, right? 3 methyls on a carbon, only 2 methyls on a carbon at a time. So if you see a carbocation, that's your ticket to rearrangement. So stop. You say, well, tertiary is pretty good. What could be better than that? Look at this over here. It's the diol. This nature of the 1,2 diol means that next door, we're going to have the opportunity for resonance if there is a shift that can happen here. So this could have been part of a ring, or it could have been a methyl. So we could do a methyl shift. And if it does, that makes it secondary with resonance, which is better than tertiary. 1,2-methyl shift. Okay, secondary with resonance, better than tertiary. So let's write that down, just as a reminder, secondary with resonance. Hey, that's not enough. I'm going to draw the resonance. Why? Because I know I need a ketone, and the resonance will give me a carbonyl. Ha, there it is. I am almost home free. Look at that. I need to neutralize. We lost water. Let's let water do the job. There we go, QED. We did it. If you didn't want to use water, you could have used more of the alcohol. That would do the job. You could have used HSO4 minus. Any of those are acceptable bases for neutralizing because they're all present. I'm going to leave you with a more challenging rearrangement. We started with the original Pinnacle. Here's one. I want you to try, and you can check with me if you don't get it, but you'll be better off trying this on your own first. Look at that guy. What does that make and why? So this is an example for you. I'm just going to give you a little hint. If I looked at that, how would you know it's a Pinnacle? Well, first of all, you should see, always say the functional group out loud. I have an alcohol. I actually have 2 alcohols. I have a diol. Am I going to do, what do I do that's special with diols? I could do oxidative cleavage, and nope, that's not going to happen. I don't have periodic acid. Oh, I do have Pinnacle conditions. I have sulfuric acid, sometimes tosic acid is used too, by the way, and heat. Must be Pinnacle. So 1, 2, 1, 2, diol. Must be a Pinnacle rearrangement. Okay, so do the same logic. Have water leave. Form something that would be favorable to expand its ring. So I want to see the ring expanded product. Okay, so I'm going to put a 5-membered ring. So draw the product that has a 5-membered ring. 4 to 5 is definitely favorable, right? Okay, that's the last hint I'm going to give. Send you off to do that to end our alcohol unit. Have fun.